السلام عليكم ورحمة الله وبركاته. يسعد صباحكم يا شباب. اليوم راح نبدأ في part 2 واللي هو بيحكي عن thermodynamics. So we finished talking about fluid mechanics. Now we'll move to thermodynamics and we'll start with the chapter 1, which is introductory part of the most important concepts and their definitions. So let me first use the pen. So the introduction, it is the science. So what do we mean by thermodynamic? It is a science that deals with heat, thermo, and work dynamics. So thermodynamics, thermo related to heat and dynamic related to the work. And those properties of substances that bear a relation to heat and work. So the word thermodynamics stems from the Greek words therm for heat and dynamics for force. Okay, as a result, we have work. So thermodynamics is a science. So maybe I'll bring you in the exam define thermodynamics. So it is a science, first of all, that is based on experimental finding. Okay. And then you can continue. It's derived from heat and work. So these findings have been formalized into certain rules. Okay. So we have experimental findings, and those findings correlate, okay, to formalized a certain rule. So energy. We'll start with the first law of thermodynamic, or we call it conservation of energy first law. So either we call it first law of thermodynamic or conservation of energy first law. So this law states that energy can't be created or destroyed, it's transformed. Okay, and I believe that all of you knows this definition. الطاقة لا تفنى ولا تستهلك من العدم ولكن تتحول بشكل إلى آخر. Cannot be created or destroyed. So this is a very good example. Here we have a rock fallen from an edge. So here at the top, at this level, so kinetic energy 0 and potential energy 10. So once it starts falling, the energy converted from one shape to another, kinetic energy start to increase until we reach here before touching the ground, kinetic energy maximum 10 maybe, and potential energy 0, almost equal to 0. Okay, so this is first law of thermodynamics or first law of conservation of energy. The second law of energy or second law of thermodynamics, energy has a quality and a quantity. Or we can say that actual process occurs in decreasing equality of energy. This is second law. Okay. So what's that mean? Energy has equality and a quantity. Let me read this statement before. So the second law of thermodynamics asserts that energy has a quality as well as a quantity, and the actual process occur in direction of decreasing quality or decreasing energy. So heat flow, for example, what's the meaning of actual process occurs in decreasing quality? It means, for example, because heat is one type of energy, work is another type of energy. So let us give you an example of heat, because you know that heat depends on temperature. So heat flows in the direction of decreasing equality. Which equality? The temperature. Okay. So for example, here if we have hot coffee, 70 degree, and the surrounding 20 degree. So how? What is the direction of heat? yes, it will transfer from higher temperature to lower temperature, from the cup to the surrounding. Okay, this is the second law of thermodynamics. Energy, maybe heat. We can say energy is heat. Okay, or it could be work. So heat or work or energy in general has quality and quantity. Okay. Another terminology is the macroscopic and microscopic views of thermodynamics. In thermodynamics, we have actually two approaches: macroscopic approach and microscopic approach. In order to define those two terminology or two concepts, let us give you this example. Here we have piston. Here we have a piston. Oh, sorry, this is cylinder. Okay, and here in the top we have a piston. And on top of this piston we have weight, certain weight, which is applied force or pressure. Okay, so as you know, any substance, here we have certain substance. For example, we have gas. This substance consists of a large number of molecules. So here we have large number of molecules. Okay. The properties of the substance depend on the behavior of these molecules. The property, for example, density. Okay. Mu, viscosity. Okay. Temperature, pressure, specific volume or volume. Okay, etc. So this property depends on the behavior of these molecules. Now, consider a gas in a container. This is the substance here, gas. In a container, the pressure of the gas is a result of so this is one of the property, pressure, is the result of momentum transfer as the molecules hit the walls of the container or of the cylinder. This is Pascal law. So it depends on the collisions between the particles or molecules and also between the molecules and the wall. Now, if you want to describe the pressure, however, we do need to know the force exerted by the molecules on an infinitesimal area on the wall in order to find the pressure. This approach, we call it microscopic. So if we go to each particle, if you wish to find the pressure for each particle for infinitesimal area, okay, this approach we call it microscopic. Now, if we attach here pressure gauge, okay, instead of this approach, it will be sufficient to attach a pressure gauge to the wall, finite area, here for example, in this position, and read the averaged or the average pressure exerted by a large number of molecules on that finite area. This approach we call it macroscopic. So what's the difference? So macroscopic tell us the average property for a substance, the average density for the whole molecules, not for certain molecule. Okay, the average viscosity, the average pressure, the average temperature for the whole system. This is, we call it macroscopic, average behavior. But the microscopic give detailed information on each particle alone. Okay, this is very detailed, very complicated. here very easier to find the average behavior of the system. Okay, that is the macroscopic approach as to thermodynamic is concerned with the average or overall behavior. Okay, so macroscopic, the overall or average. This approach is called sometimes classical thermodynamics, and usually we adapt this approach. Or yes, this is what we'll do in this course. We'll adapt the macroscopic, the average behavior. On the other hand, the microscopic approach to the thermodynamic, known as statistical thermodynamics, is concerned directly with the structure of the matter. Okay, its objective to find by statistical means the average behavior of the particle making up the system of the particle itself. This approach is involved, very involved, dig deeper, okay, and is not used anymore in the remaining of this course. So we'll not use this approach. Okay. Instead, the macroscopic approach provides direct and easy solution to engineering problems. Okay. So we'll adapt macroscopic. What's the difference? You have to know by now the difference between macroscopic and microscopic. Thermodynamic system. How we can describe it. Before talking about thermodynamic, an important step in any engineering analysis is to describe precisely what's being studied. So we must give general description for our system. For example, in mechanics, for example, in statics or in dynamics, if the motion of a body is to be determined, figure 1, this figure, we need to find out the motion of this body. The first step we did is to do free body diagram. Okay, so the first step is to define free body diagram. And the second step is to identify all forces exerted on it by other bodies, like friction here, okay, and normal force, and external force from here, from the handle or from the cord. Then we'll adapt one of the laws, for example, Newton's second law, in order to solve and to find the unknowns. This is what we used to do in mechanics. This is just an example that how we describe the system. Now, in thermodynamics, the term system is used to identify the subject of the analysis. For example, here the cup of coffee, if we care about the coffee, then we'll call the coffee as system. So coffee in the cup, we call this coffee system. This is our system. So once the system is defined, so we define first of all the system. So sometimes we come and draw control volume. This control volume, as we mentioned earlier in fluid, differ than this control volume, which care about what's inside the cup. So this control volume, the smaller one, cover the coffee only. So this is our system. Now, if this is our control volume, the greater one, then our system is the cup and the coffee inside. Okay, so the first step is to define our system. Where is our system? By drawing control volume. We'll talk, I explain control volume again in the coming slide. So once the control volume is defined and the second step, relevant interaction with other systems are identified. For example, the surrounding 20 degrees Celsius. And here, cup of coffee, 70 degrees Celsius. So there is interaction, yes. There is heat loss from our system to the surrounding. Our system decouple, okay, to surrounding. This is interaction. One or more physical laws or relation are applied. So first, describe the system precisely. Then you will know which equation you can apply, which law you can apply. Open system versus closed system. I think you are by now familiar with these two terminology or two concepts. Open system. So what is first question? What is the difference between open system and closed system? So I'll give you 5 seconds to think. Yes. So here you can notice that we have two balloons. This balloon open to atmosphere, so we draw control volume or control surface. This is control surface. Okay, dark color, and this balloon closed. So we draw control surface here. So this dashed line, we call it control surface, and what is inside is control volume. Okay. Now, what is the difference between open system and closed system? Open system, we have mass n, and mass out. Okay, this is mass n, and here we have mass out. But in closed system, closed one, we don't have mass in, mass out. This is the first difference. Here in the open system, maybe we have energy in, energy out. Energy in, energy out in terms of work or Q. This is energy in or energy out. Closed system, do we have energy in, energy out? Yes. We have energy in and energy out. So this is something common between closed and open system. So energy, it could be heat, it could be work. Yeah. So here is example of energy or a closed system. Closed system, or sometimes we call it control mass, because mass is controlled. There is no drop in the mass. The amount of the system remain closed during the process. So here we have cylinder, piston cylinder, and here inside we have gas. So this is state 1, and here we have state 2. What is the difference? We add heat. So as long as we add heat, what will happen? Gas will expand. The volume increased from 1 up to 3 meter cube. Okay, 1 and become 3. So because we add heat, okay, the volume expands. So in general, the closed system or control mass system, we have no mass crossing the boundary. So here we have control surface, as you can see, dashed line. Okay. So mass remain constant, m constant. Control mass, m remain constant. Okay. But do we have energy? Yes, we have energy. So a closed system refers to a fixed quantity of matter. For example, we have a fixed quantity of gas. State 1, we said, and this is state 2. So the amount of gas remain constant during the process, during transfer from 1 to 2. A closed system is used when particular quantity of matter is under study. A closed system always contains the same matter. Gas remain gas. Nothing will enter or crossing the boundary. There can be no transfer of mass across its boundary. Yes. And here we have explanation, those statements, explanation of what do we have in here, and I already explained. So the main feature of closed system, there is no mass in. Open system, or we call it control volume. We are controlling the volume. An open system is a properly selected region in space. Okay? It encloses a device that involves mass flow. There is mass flow in and out, such as nozzle, compressor, turbine. Okay? Here we have 3 examples of open system. Okay? In the closed system, we have a very good example of piston cylinder with no mass crossing the boundary. Flow through such devices is best studied by selecting the region within the device as a control volume. Both mass and energy can cross the boundary of the control volume. There are no concrete rules for the selection of the control volume. So some of you, if we have nozzle for example, okay, some of you say I want to take my control volume to be here. Some of you take the control volume like this. So there is no concrete rule, okay, for the selection of control volume, but proper choice makes the analysis much easier. So either your selection will make the problem easier or it will be difficult to solve. Now, the boundary of the control volume is called the boundary surface. Okay, as I'll show you to you know why. The boundary surface can be real or it can be imaginary. Control volume can be fixed in size and shape, or it may involve a moving boundary. Let's see example. So here we have a nozzle. Okay, so we'll draw a control surface. Inside this control surface, we have control volume. Now, the lines beside those walls, the walls of the nozzle, we call it real boundary. Here, the boundary of cell can be real or can be imaginary. So those boundaries are real. Now, those boundaries, because there is no surface, we call it imaginary boundary. Okay, so this is the meaning of imaginary boundary. Now, control volume can be fixed or can be moving. So here, for example, we draw control volume. Those control or control surface or boundaries adjacent to real or fixed surface, but the one beside the piston here we call it moving boundary. Okay, this boundary, the dashed line here. Okay, now this boundary, there is no adjacent wall, then this is imaginary boundary. Here another example. This is a boiler. Okay, this is a good example of open system control volume with one inlet, one exit. So cold water comes from the tanks accumulated in here, and this is the exit. So we have inlet, we have exit. We choose the system to be only water. We call the hot water or the water inside this boiler is our system. Okay, and we have inlet, we have exit, then this is open system. So that's it for today lecture. Next time on this lecture for Tuesday. Now we have another lecture will be on Thursday. So today, the date of this of tomorrow, it will be 18. or sorry, today is Tuesday. Sorry for that. So today is 17th of March. So I have to read it. Then on Thursday we'll have on 19th of March we'll have live lecture. Okay, live lecture. So make sure that you prepare the whole material uploaded for you on the Moodle. So if you have any question, you might ask me on Thursday lecture. Thank you for listening and see you